Hi there, welcome to your lesson on optimization. Okay, this is a big topic in this unit and in upcoming units as well. Let's take a look. We're going to begin with this problem here. A gardener has 24 meters of fencing to make a vegetable plot. Okay, if the length of the plot is x meters and the width is y meters, show that y equals 12 minus x. Okay, give that a try. Given this 24 meters of fencing, see if you can make this happen. Let's take a look at that. So here's our rectangular plot. We said it has a length of x and a width of y. And then we're also told that the fence in total is 24 meters. So this would be 24 meters. So that's like a perimeter situation. We know the perimeter is made up of two x's and two y's like this. So perimeter is 2x plus 2y, right? This and this, and then this and this. But we also know that perimeter must be 24. So 24 equals that. We can see an equation emerging that might turn into this one. We're trying to solve for y here. So I'm going to divide everything by 2. That means 12 equals x plus y. And now move the x over, I'm solving for y. So y equals 12 minus x. And we got to that point. That's an important thing that often happens where we have an equation here, and we have two variables, and we want to simplify it using some extra information so that we have the lengths and widths in terms of one variable. So it's always easier to have one variable representing things. So now we know this is x, and let's go back to here. This is x, this was y, but now we figured out y is 12 minus x. So now we can look at length and width with those, and they have the same variable, which is going to make things easier. So number 2, find an expression for the area in terms of x. See, the area, normally we'd say area is just y times x, but now we have this here and we can write an area in terms of x only. So area is x times 12 minus x. Instead of saying x times y, we can say x times 12 minus x, and now we have an equation in terms of one variable, which makes it much easier to work with. Okay, plot this on your GDC and then find the maximum value for area. So we've done this a lot already. This is going to be a quadratic function or model. Put it in your calculator, find the maximum point, which will give us the maximum area. And then answer what dimensions of the plot give you this maximum area. So here's our area model taken one step further. If you wanted to, you can multiply to get this. Put that on our calculator, we should get this graph here. We can see the maximum point here. And we know since this is like our y value, that the y-axis here is area, and then this is x. On the x-axis we have x, which is actually the width, right? So we have that model here. We know our maximum area will be here because we can see that's the highest area. So what was that point? Did you find it? Okay, that point should be 636. That tells you at an x value of 6, the area is 36. That's our maximum area. So what are the dimensions of the plot of land? Well, this is what optimization is all about. We have found this maximum point, all right? So the maximum area is 36, and that occurs when x is 6. And if x was 6, then y would be, well, we can put x and 6 in here, and we find out y is also 6. So that is what optimization is all about. It's about optimizing, which often means what is the maximum thing we can get or the minimum thing. That's optimization. It's the optimum solution, the optimum situation. So with a limited amount of fencing, our optimum situation would be getting what is the maximum amount of area we can get with that limited fencing, right? Because of course we can use that 24 meters in other ways and get a smaller area, but why would you want a smaller area? You want to maximize the area. That's the optimum situation. So that is what optimization is, finding the best possible situation. Let's look at this in another problem. So let's say we have this, and we're familiar with this problem. We've seen it a bunch of times already. This is a classic problem, but it's a really great one to illustrate how volume becomes a cubic model. So we have a box made from a piece of cardboard measuring 6 by 9. So this would be 6 centimeters, 9 centimeters. And then squares measuring x by x are cut from the corners. Everything's folded up to make this box. Show that the formula for the volume, we're trying to show the volume is going to work. Okay, first of all, we know this is 9 minus 2x because this entire length was 9, and now we're subtracting this x and this x. So from here to here must be 9 minus 2x. And over here, likewise, we have 6 minus 2x because the entire length was 6, and we're cutting away this piece and this piece. So now there's remaining length here is 6 minus 2x. Great, so our volume then is x times 9 minus 2x times 6 minus 2x. We're multiplying this side, this side, and the height. And now we know this, and then the x is our height here. So that's our volume. All right, now plot a graph and hence find the maximum volume. So now if you plot this on your calculator, you should be able to find the max point. And the max point is this whole idea of maximization, sorry, of optimization. We want to optimize this box by getting the largest volume. So the maximum point on the volume function will be the maximum volume. So what is our optimum volume? What should we do to the x here to get that optimum or maximum volume possible? Well, once you've graphed it, you should see this graph on your calculator. It has a maximum point, it has a minimum point. So if we say we want to optimize the volume, we want to find the maximum volume. So y values here are volume, and we can see the max is here. The maximum occurs at 28.5. Sorry, that is the maximum volume. And that occurs at some x value. So I don't know if I have it here in the solution, but what x value produces it? Hopefully you saw that on your calculator as well. It looks like something like 1.3. So if you cut off like 1.3 or so from here, then you would have that optimum volume. Great, let's look at another one. So we've learned that different models can be used to optimize real-life problems. When you are finding an optimal value, it can be a maximum value or a minimum, because sometimes the optimal solution or the best thing that you can do in a situation is to get the smallest amount, not the largest, right? We've seen two maximum, but let's look at a minimum one now. So the situation is this, and this is also familiar. We looked at this one last time. Find the minimum surface area of a closed cylinder with a volume of 500. So why would a minimum surface area be optimal? Let's think of it this way. Let's say you're making products and you have to make a can for like some food products, and you want to make sure your can fits a certain volume. You want to put a certain amount of food in there. Let's say this is I don't know, beans. You want to put 500 cubic centimeters of beans in there, but you want to minimize the surface area, because by minimizing the surface area, you're minimizing how much like aluminum or tin or whatever metal the can is made out of, you're minimizing that amount. So it's going to cost you less as a company to produce that, right? So here the optimal would be to get that minimum surface area. So let's see if we can get this one sorted out. We're told the volume, but we need the surface area. So we're going to have to flash back for a moment and look back at something we looked at last time, which is what are the volume and surface area of a cylinder. So you remember that volume is like stacking bases, right? So if we stack up all those bases, and that's the height of those stacked bases is the height of the cylinder. So the volume is base area times the height, which means area of a circle, pi r squared, times the height. So it's that circle times that many times gives us the volume, right? That's how volume works. And surface area was, you have a circumference here. That circumference is 2 pi r. That is the length here. If you unwrap that, that is 2 pi r. Then this is the height. So that's the height of the can or the cylinder. And then we have two bases, and each one is pi r squared. So the surface area would be 2 pi r squared, two of these circles, plus this surface, which is a rectangle, and the area of that rectangle is h times 2 pi r right here. So that's our surface area of a cylinder. Now let's use those formulas and proceed with the problem we have. So we have that situation. We want to make we want to use the volume to find a minimum surface area. So the equation we want to minimize is the surface area one. So let's begin with the volume, because we're going to use that to help us create another equation for surface area. So volume is base area times height, so pi r squared times h. In this case, our volume is 500, so we have this. Now this can be solved for h, because we know our surface area formula also has h, and it also has r, but we can solve this for h pretty easily. We can divide 500 by pi r squared and get h. Now that will be valuable in the next step, because now I'm looking at surface area. This is the equation we want to minimize, but this equation has r as a variable and h as a variable. So there's two variables here, so we can't graph that. We need this to be surface area in terms of one variable, and the easier one to replace here is h. So that's why I solve for h here, so I can put that in here now. All right, so I use one equation or one given information to help me make a better equation here. So now that h will be replaced with this, and this will become a new surface area equation in terms of r only. So what happens when you multiply this and simplify? You can cancel some stuff. What do you get? Well, you can cancel the pi, you can cancel an r in one of the r's here, and then a 2 times 500 is 1,000. So one r remains, and there it is. So there's our simplified surface area formula using the bit of information about the volume. Now this is in terms of one variable, so we can graph it. So graph that now and answer the question, what is the minimum surface area? And what is the radius that helps us get that minimum? All right, the graph should look like this. So check your graph. You should have something like this. And then looking at that graph, we know this is surface area because that's S here. Our Y value is here. And then R is here along this axis. So at this radius here, we have a minimum volume, sorry, surface area right here. So it's that point there. There's our minimum. That tells us at 4.3, we have a minimum surface area of 348.7. So we found out exactly what the radius of this can must be to give us a minimum surface area. So that could be good for a company to know that. And now we know it will still hold the 500 cubic centimeters we need it to hold. Pretty good information, good problem. All right, so do I have more? Yeah, maybe. Let's see what's next. Okay, try this one out. Similar kind of problem, but now you're given the surface area and you're asked to find the maximum volume. So it's like flipped around. This time you start with the surface area, and then the thing you want to minimize or maximize or optimize is your volume. So you're going to do this one a little backwards. Start with surface area and then substitute into the volume formula so that you can then optimize that one. All right, so here's volume. We're told, and then there's surface area. We are told the surface area is 5,000, so I put that there. Now we know we need to work with our volume formula, and again it might be easier to substitute H, so I'm going to solve this one for H. That might be tricky. Try it now. So to solve it for H, I did 5,000 minus all of this there, and then I divided by 2 pi r, and then I have H. So now I have H. That can go into the volume formula. What happens to that when it's simplified? Let's try. So there's the H replaced by all that in the volume formula. Now to simplify this, when you multiply this, the pi will cancel. One of these r's again will cancel. You'll be left with just an r out here. So there's the r. Now the r is going to multiply this. So I get 2,500 r because I'm dividing by 2 also. So there's 2,500 r. And then r multiplied to here. Also these 2's cancel because you're dividing here by 2 also. But that r multiplies in there, r cubed. So check your algebra there. We have this volume formula. It is now in terms of one variable, r, which is what we need. All right. And since it's in terms of one variable, we can now graph it and talk about max and min volumes, all right, because that's what we needed. So let's check. So you're graphing it. And this is what the graph should look like. Here's volume, which is our y value. Here's r, which is our x value, right? So at a radius of, look, it says here, you get a volume of, 16.3. Is this even the right graph? Something doesn't look right there. The height, this might not even be the right. No, the radius. Oh, okay. So the maximum volume is here. It looks like a very big number, 20, I don't know, 28,000 or something. But the radius that produces that is 16.3, and that's what we have here. So that would be the optimal radius. It also gives the height. So I think it took the radius and it plugged the radius back into the formula for here, and we could put in, or here even, you can put the radius value in there. In here, let's say, and then you can find the height. So then you know the optimal radius and height to produce the maximum volume, which is this number here that I don't have. Okay, great problem, great math if you're able to do that, for sure. All right, so that's the kind of problem we should be able to deal with now. Let's try some more when we see each other together next class. See you soon.